Okay, so we have the notes for section 8.5, polar equations of conics. So just a reminder about eccentricity. So a conic section is the set of all points in the plane whose distance from a particular point called the focus and a perpendicular line called the directrix in the plane have a constant ratio. So this figure down here, we assume that the focus does not lie on the directrix. So this ratio, PF to PD, determines the eccentricity. So PF divided by PD is what the eccentricity is. Depending on what that value is, determines what kind of shape you have. So if that eccentricity is more than 1, you have a hyperbola. If it's exactly equal to 1, you have a parabola, which if you remember the definition of parabola, a parabola is all set of points equidistant from the focus and the directrix, so it should be exactly 1. And an ellipse if it's less than 1, which means that it'll close the loop. Okay, so writing polar equations for conics. So to obtain a polar equation for a conic section, we position the pole, so the origin of the polar system, at the conic's focus, and the polar axis along the focal axis with the directrix to the right of the pole. So there you go. So there's your polar axis, there's your pole, there's your directrix. So if you have eccentricity of less than 1, you end up with an ellipse because PF is always less than PD. If it's exactly equal, you have a parabola. And if PF is more than PD along every point, you have a hyperbola. Okay. So here are our polar equations for conics. There are kind of 4 generic ones we've got here. So you've got this equation. So here are your 4 versions, whether it opens left or right or down or up. So where the directrix is relative to the focus, and then your generic equations. So if you see sines, it's going to run up and down. Cosines run left and right because cosine is the x direction, sine is the y direction. So these are your generic things to fill in. Okay, so example 1, given that the focus is at the pole, I'll write a polar equation for the specified conic and graph it. So eccentricity is 3/5, directrix is x equals 2. So this is an example of a x equals k, positive number. So this is going to have this form, ke over 1 plus e cosine. So our generic equation is so there's our k value. There's our e value, so 2 times 3/5 over 1 plus 3/5 cosine theta. Which comes out to be, so that's 6/5 over, and what I can do is I can multiply by 5 over 5 on the top and bottom. That'll get rid of these fractions inside fractions. So this will be 6 over 5 plus 3 cosine theta. So there you go, r equals. So for this one, our k value is -2. So we're looking at this version, 1 minus e cosine. So let's see here, r equals k times e over 1 minus, since k is negative, we get the minus in between, e cosine theta. So -2 over 1 minus 1 cosine theta. Or just -2 over 1 minus cosine theta. Whoops. There we go. All right. Directrix y equals 4. So I got a positive y value, which means I'm going to have a plus sign on the bottom. So r equals k times e over 1 plus e sine theta. So that's 12/12 over 1 plus. Now, it is possible to reduce this, but you still have the fraction here. Since I'm over 12ths, I want to multiply the top and bottom by 2s to get rid of the fractions everywhere. So that would be what you'd have. Now, I'm not going to graph it, but we can label it. So this eccentricity is less than 1. So that means that we have and this will graph an ellipse. The second one, the eccentricity is 1. This will graph a parabola. Eccentricity of more than 1. This will graph a hyperbola. And let's actually see if I can get them to graph, actually. I'm not going to draw by hand. So make sure we're in radian. Go to the graph. Change the type to r equals. So let's try 6 over 5 plus 3 cos theta. There's my ellipse. So let's try the second one, negative 2 over 1 minus cos theta. So there's our hyperbola. Sorry, parabola. Oh, whoops, that should be a positive 2. The k value is always, whether k is a negative number, it just tells you whether that's a plus or minus. The k is the absolute value of that. So that's actually backwards. No, whoops, I did graph it right. Did I? Oh no, put the negative sign all the way up front. That should be it. Directrix at negative 2 over here. The last one would be, whoops, 12 over 2 plus 3 sine theta. So there's your hyperbola. If you notice, it kind of draws it out of order. All right. So analyzing polar equations, so determine the eccentricity, the type of conic, and the directrix. So let's see here. So since our default formulas have 1s here, we need to divide the top and bottom by 2s. So it needs to look like this. So r equals 3 over 1 plus 1.5 cosine theta. So E is equal to 1.5, because that's just this number. That up there is KE. So that's going to be, so K times E is 3, which means K times 1.5 is 3. So K is 2. So the eccentricity, we already found 1.5. The type of conic, that's more than 1. So it's hyperbola. And the directrix is going to be, since this cosine is going to be x, since this plus, it's going to be positive 2. There you go. So over here, we got to divide everybody by 3, by 4, to turn that lead term into a 4. So we get r equals 3 halves over 1 minus 3/4 sine theta. So that's our eccentricity. Less than 1 means that this is an ellipse. This is sine, so my directrix is y equals, and it's going to be, oops, can't do it yet. The top is equal to KE. I know E is already 3 halves is equal to K 3/4. So this means K is 2. Since the subtraction sign in the middle, the directrix is at negative 2. The sign in here is always the sign of the directrix. Okay. Example 3, analyze the conic section given by the equation. Let's rewrite it here. R equals 16 over 5 minus 3 cosine theta. Okay, so let's see here. So the eccentricity, if I divide everybody by 5, is going to be 3/5. To find A, B, and C, we're going to need to look at the graph. So we got 16 over 5 minus 3 cos theta. Draw. There we go. So if you look, actually kind of hard to see because it's not focusing on my screen. It's focusing on nothing right now. But this axis is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units wide. So 2a is equal to 10, which means a is 5. And if you look at your short distance, we can figure out what 2b is. 2b is 1, 2, 3, from 4 to negative 4. So that's 8 units. So b is 4. All right. And then we know that since this is an ellipse, we know that a squared is equal to b squared plus c squared. So 25 is equal to 16 plus c squared. Let's get that out of the way so I can get to focus again. There it goes. So c squared is 9, so c is 3. So if I actually want to write this, this would be x. Yeah. So let's say, so we can figure out where the center is. Can you figure out where the center is? So the ellipse runs from, that's negative 2 over here. That's positive 8 over here. So halfway between those is at 3, 0. So it's going to be x minus 3 squared over bigger 25 plus y squared over 16 equals 1 if you wanted the Cartesian version. Okay, so orbits. The pole can be thought of as the center of a large body such as the sun, with a smaller body following the conic path, because in orbits, the sun, the heavier object, sits at one of the foci. The coordinates given by a polar equation are the distance r between the two bodies and the direction theta from the larger body to smaller body, path of motion. So an ellipse with eccentricity of e, semi-major axis a, so half. So remember, semi-major axis is half of the long distance. So let's see here. Using the data from the table below, find the polar equation for the orbit of Mercury. Use it to approximate that planet's aphelion, farthest distance, and perihelion, closest. Okay, so for Mercury, we're going to have r equals, so semi-major axis, so 57.9, 1 minus 0.2056 squared over 1 plus 0.2056 cosine theta. So let's see here. Is there any tricks here? So the closest distance, well, the two distances are going to be when cosine is largest or smallest, so either 1 or negative 1. So what I need to do is when I just need to figure out so when cosine theta is equal to 1, r is equal to, and when cosine theta is equal to negative 1, r is equal to. Because if cosine is 1, that makes this denominator as large as possible, so the whole fraction is as small as possible. So this is going to be the, whoops. No, we'll figure it out. We'll just look at which one's smaller, which one's larger. That's actually going to be the perihelion. But anyway, menu, go back to the calculator mode. So we have a fraction with 57.9 times 1 minus 0.2056 squared over 1 plus 0.2056. So this comes out to be about 46 gigameters. We can do the same thing. We could just change this to a minus sign. Whoops, minus sign. Awesome. negative sign. I get 69.8 gigameters. So this is right here, this is perihelion, closest distance. This is aphelion, farthest distance. Because the bigger the bottom number is, the smaller the value is. So that's the closest. So you divide something by a bigger number, the number gets smaller. So that's the closest you can be. And that is the end of the section.